Welcome to section 8.3 today, class. Today we're moving on to talking about all rational functions. In the first piece, we only talked about reciprocal functions, which are a specific type of rational functions. Now we're branching out to cover all of them. And when we're covering all of them, there's a lot of vocabulary that we're going to need to know. So the focus of today is mainly getting you to understand that vocabulary and how to calculate the pieces of that vocabulary. The first vocabulary word we're going to talk about are points of discontinuity. Now, a point of discontinuity, that comes from when the denominator equals 0. All right, so it comes from when the denominator, the bottom of your rational function, when it equals 0, that is going to create a point of discontinuity. There's three things that can happen when we're talking about these points of discontinuity. The first one is where there just isn't. It is a continuous function. Well, let's take a look at why that would occur, what that looks like. So again, these occur when the denominator equals 0. All right, so I'm going to take the denominator, set it equal to 0. Well, notice what happens. If I subtract the 1 over, and I try to square root both sides, well, notice what happens. I'm not getting a real number. So what that means is there's no real number that would make that denominator 0. So when the denominator can't be 0, there's no number that makes it 0, we're going to say that's continuous. There's going to be no breaks in that function. Now, the second type, creating a hole. This is also known as a removable discontinuity. Now let's look at why. So again, I'm taking that denominator, and I'm setting it equal to 0. So I'm getting a discontinuity at x equals -2. All right, there's something going on there. Well, in this first type of discontinuity, the denominator can equal 0. So here we're getting a discontinuity at x equals -2, but it cancels out. What that means is notice that factor of x minus 2. It actually cancels out, and this just becomes y equals x plus 3. So notice the graph. Notice the graph is of the line y equals x plus 3 because that x plus 2 factor cancels. However, because in the original denominator you couldn't have x be -2, it creates a hole there. So when you have that denominator, you can set it equal to 0 and find a point of discontinuity. But when it cancels out, that creates a hole in your graph. You graph the new and improved function, the reduced function. However, there's a hole at that x value where that factor used to be. And now the final type, a non-removable discontinuity. We're still going to set the denominator equal to 0. So x minus 2 equals 0. So there is a discontinuity at x equals 2. But this time, notice, it doesn't factor out, okay? There's nothing we can do to remove that factor from our equation. So in that case, when it can't be removed, what ends up happening, that is when you create a vertical asymptote, when the denominator equals 0 and it can't be removed. This is what you're more comfortable with. This is what you've seen before in our previous sections of this chapter. But now here's the explanation why. The difference between a hole and a vertical asymptote. A hole is created when you can remove that factor. An asymptote is created when you cannot remove that factor. All right, so our steps to finding those points of discontinuity. The first step, factor both the numerator and the denominator of the rational expression. Then set each factor equal to 0. Those are your points of discontinuity. And again, select each factor. I should clarify in the denominator equal to 0 and solve. Cancel out any possible factors and then use a table on the previous page to determine the type formed. Again, if it cancels, it makes a hole. If it doesn't cancel, it creates a vertical asymptote. And the domain of all these is going to be all real numbers except where that point of discontinuity is. So our domain is going to be all real numbers, again, except where those discontinuous points are. When I'm asking for the x-intercept, okay, that's going to be in this form. And how you calculate that is set the numerator equal to 0, and then you solve for x. When you're looking for the y-intercept, so something of that form, you plug 0 in for x, and then you solve for y. Now again, I know this is a lot to take in one thing. So that's why I highly encourage you, as you're going through your practice work, make sure to have this out, because this will help you through it, because there's a lot of vocab and a lot of different things you have to solve for. So as you're practicing, make sure you have this out. So let's take a look at some examples. So part A says I want you to find the point of discontinuity and the domain. All right, so the point of discontinuity are going to occur where those factors in the denominator equal 0. So where x equals 2 and x equals 3, those are going to be our point of discontinuity. All right, wherever the denominator equals 0, we create one of those points of discontinuity. And that means that my domain, all real numbers, except x can't be 2 and x can't be 3. So that's part A to all of these. Again, just making the denominator equal to 0 and then saying the domain is all real numbers except at those points. Part B, the type of discontinuity. Well, neither one of these canceled. All right, neither one of these points were canceled out. So that means both of them are going to create a vertical asymptote at that point. That x value will become a vertical asymptote. And again, the reason I know that is because neither of those canceled out. If they canceled out, then you would have a hole instead. But because they didn't, vertical asymptote. Part C, the x-intercepts. Now again, the x-intercepts, let's go back and reflect what creates that. X-intercept, set the numerator equal to 0 and solve for x. All right. So set the numerator equal to 0. So set that x plus 1 equal to 0. Solve. There is our x-intercept. So again, it's not difficult. It's just you have to remember that's what you have to do for an x-intercept. It can get a little bit tricky as you're having to work through all these different steps. And finally, step D. For the y-intercept, you plug 0 in for x and then solve for y. So on the top, you put 0 in for x. That gives you 1. 0 in for x gives you a -2 and a -3. So our y-intercept is going to be at 0, 1/6. So again, there's a lot to take in here, all right? A lot of vocab, which is, again, why whenever you're doing practice work on this, have this out so you can reflect how to solve on each piece. So moving on to our next one, and I'm going to color code these the same way so you can see the steps. 1, find the domain and point of discontinuity. Well, again, that is where you take the denominator, set the denominator equal to 0. So what this is saying is that there is a point of discontinuity at x equals 4. So the domain is all real numbers except where x equals 4. For part B, now we have to label the type of discontinuity. Well, in order to do that, we have to factor this. So if we factor this, we get x plus 1, x minus 4, x minus 4. I want you to notice it canceled out. Okay? So, because it canceled out, that means that we are getting a hole right there. All right? That's what it means. So, now we have a hole sitting there at our at that point of discontinuity. Part C, the x-intercept. The x-intercept is where you set the numerator equal to 0 and you solve for x. All right, now, because we canceled off those pieces, when we're looking for x-intercepts, okay, you actually don't include that value in the x-intercept. So I only have to worry about setting the remaining piece equal to 0 because we know we can't use the other one anyway. So we get x equals -1 again. And again, that x minus 4 can't create an intercept because it is creating a point of discontinuity. Step D. Step D, y-intercept. So again, this is where we are setting, or we're plugging 0 in for x. And again, we only have to worry about our simplified equation of y equals x plus 1 when we're plugging in 0 for x. And we get that for our y-intercept. All right, let's keep chugging away at these. So part A, again, is finding our point of discontinuity. Well, look what happens when we set the denominator equal to 0. We try to solve it. However, when we have to take the square root of -1, we're seeing that there are no points of discontinuity. There's none, okay? And so that means the domain is legitimately just all real numbers. Well, if there's no point of discontinuity, that means our part B is kind of null and void. Because if there aren't any points of discontinuity, we can't label what type of discontinuity they are. So we don't even have to do B because there are no points to label. So that means we just get to jump to C, finding the x-intercept. And again, finding the x-intercept is taking the numerator and setting it equal to 0. So I get an x-intercept at 5, 0. Now remember the y-intercept. The y-intercept is where we put 0 in for x. So we get -5 on top, 1 on the bottom, so we get -5 for our y-intercept. All right, one more example of this type to show you some other things that can happen. So part A, finding the point of discontinuity. Well, that bottom factors, so we're going to have to worry about that. So remember, this pattern is a difference of squares pattern. So that is how I'm going to be able to factor that bottom. So when I take those pieces and set them equal to 0, I get 2 points of discontinuity at -4 and 4. So that means my domain is all real numbers except x equals 4 or x equals -4. Again, your domain is always all real numbers except where those points of discontinuity are. Oh, part B, labeling the type. Well, here, neither canceled out. So because neither canceled out, both of them are actually creating vertical asymptotes. Okay, again, wherever there's a point of discontinuity and it doesn't cancel, you end up with a vertical asymptote there. Part C, your x-intercepts. Again, your x-intercepts are where you set the numerator equal to 0. Well, here we have kind of an issue with that, because when we set the numerator equal to 0, it can't happen. There's just a number up there, and a number can never equal 0. So what this means is that there's actually no x-intercept. So when that happens, that's all that it means. No x-intercept. And then finally, the y-intercept. When I plug 0 in for x, oh, let me write that a little bit nicer. I get a positive 4 and a negative 4. So that gives me a negative 1 over negative 16 for my y-intercept. All right, so again, I realize that is a lot to take in, a lot happening there. But hopefully my color coding helped to keep all those pieces straight. And again, when you're doing these, you absolutely have to have this out to remind you how to do these problems. All right, horizontal asymptotes. So there aren't just points of discontinuities we have to worry about. There's also horizontal asymptotes. Okay, and again, you've seen those already in the first couple of sections, but we're going to learn some general rules for dealing with all of these. Now, these are much, much easier than what we've done so far today. The horizontal asymptotes, they're determined by comparing the degree or the highest power of the numerator to the highest power of the denominator. So that's all you're doing here. So let's take a look at these. When the degree of the numerator is less than the denominator. So here we have a degree of 1 over a degree of 2. So when you have less over more, your horizontal asymptote is always at y equals 0. Always. Okay? And another thing to keep in mind, horizontal asymptotes always are in the form y equals a number because they're horizontal. When the degree on top is higher than the bottom, so here we have a degree 2 over a degree 1. When that's your case, you have no horizontal asymptote. Look at that graph beneath it. There's no horizontal line that your graph is approaching. So we say that there's no horizontal asymptote. More over less is none. Same over same. Well, here's a degree 1 over degree 1. When the degrees match, you take the ratio of their leading coefficients. So 2 divided by 1, that's going to give you a horizontal asymptote up at 2. All right, so again, I think these are easier. It's just something you have to remember those little rules to get these. So let's take a look at these. So I need to compare the degrees. So here's a degree 1 over a degree 1. So when the degrees match, let's take a look. When the degrees match, that means I'm looking at that case. Same over same means I need the ratio of the leading coefficients. So I need negative 2 divided by 1. That's going to give me a horizontal asymptote at the line y equals negative 2. For this next one, I have a degree 1 over a degree 2. So I have less over more. Less over more means it is automatically at y equals 0. Here I have a degree 2 over a degree 1. More over less, our last case is right here, and we don't have any horizontal asymptote when that occurs? Absolutely none. All right, so that's the end of our notes today. And again, I realize that is a lot to take in. So please make sure you have all this written down. Come back ready so you can use our class time meaningfully to work on your practice work.